But for something very small like an atom, which has a diameter almost as wide as its wavelength, if you determine the accuracy in its position to 1/1,000,000th of a meter, you are accurate in its velocity to plus or minus 1,000 meters per second. Not very precise at all. And that is because it is so small that the particle's size is on the same scale as its wavelength. We cannot, therefore, for small objects, know their position and their speed with great accuracy at the same time. So now we're going to go back, understanding that small particles have a wave nature that can affect how they behave, and look at the double slit experiment again. What if you redo the double slit experiment and fire electrons or photons at the slits, but one at a time, and record the outcome on a photographic plate after thousands of trials? What do you think happens? It turns out that you get the wave pattern. Now how can that be? The electrons are approaching the two slits one at a time. If they are behaving as waves, what on earth are they interfering with? Apparently, a single particle, like a photon or electron, can interfere with itself and must be going through both slits at once. Okay, maybe we can try and observe it going through both slits at once. Then we have proof of what the particle is doing. If we put a little meter by one slit, as represented by the eye looking at the right slit in this picture, it should register the particle passing through it. We should register the particle going through this slit every single time and see the wave pattern on the far screen, right? So the scientists tried this. You know what happened? The particle was detected passing through the slit only half the time. And to the scientists' shock and surprise, the pattern on the far screen changed to the particle pattern, just by trying to watch the particle. This can be very frustrating, but it is reality. So what we get from this is that very small particles have a waviness to them if they are unobserved. That waviness means they occupy an area of space and can be anywhere in that area of space. Since it occupies an area, it can pass through two slits that are close together, both at once. That means small things may have many different positions or orientations, and only the act of observing them gives the particle a single position. Once you observe the particle, it collapses to occupying only a single point, and can only pass through one slit. The fact that someone is looking is very important. Because we cannot pin down the location of extremely small particles, we do not know where they are until we observe them. The act of observing a small particle removes its wave nature. Unobserved, very small particles have a series of probabilities of being present in different places when moving from point A to point B. The lesson? Every unobserved particle moving from point A to point B literally takes many routes to its destination. It doesn't make a lot of sense, but this is what's happening. It's the only way to explain the data. So now we have to use this logic in understanding the early universe. This is the hard part. Don't be afraid to say you don't understand or it doesn't make sense, because it probably doesn't. However, mathematically it is accurate and physically the truth. The universe was smaller in the past, and at one time it was quantum scale small. This means it would have expressed the same weird quantum behavior. Being that small meant that it could exist in many, many different orientations and shapes and forms, all with the potential of being real until it was observed. And it is observed today. For something like our universe, being very small and unobserved meant that not only did it not have a specific position, it did not have a specific value for things like proton mass, electron charge, and speed of light. It had the ability to have many different values for these all at once, until it was observed. That's us observing it from today, which you can see on the right. Then the universe collapses down to a single point with single values for proton mass, electric charge, speed of light, and all those other variables that are now fixed. So now let's try and apply these quantum rules to what an early, small, quantum-sized universe would have been like. Rule 1. Everything in the universe is both a wave and a particle at the same time. Rule 2. When it was very small, smaller than an atom, the entire universe behaved like both a wave and a particle too. Rule 3. In any 26-dimensional universe like ours, there are 10 to the power of 500 different states that the universe could have started in as a quantum-sized particle. That's because it was small and wavy and unobserved. Each of these different states would have had their own unique values for things we talked about in the strong anthropic principle, like strengths for gravity, electrical force, proton mass, and any other physical feature of this universe you could imagine. And they would have all existed at once, because nobody was looking. This gets us around that there was only one universe, because if there are 10 to the 500 equally real universes to start, and if the probability of having one with our physical constants is anything greater than 0, then it will occur. We now have a lot of trials at a universe, and low-odds events like the formation of our universe, which is stable and can support life, must occur. We still, however, haven't figured out why there is something instead of nothing at all. For this, we need another weird quantum rule. Particles can literally come into existence out of nothing, as long as they disappear again very quickly. It would take a long time to explain why this is true, but it has been demonstrated in experiments. Particles like protons and electrons literally appear out of nothing and then vanish again very quickly all the time. If the universe was once quantum-sized, it would have behaved this way too. The entire universe would appear out of absolutely nothing. This isn't seen with objects our size, because the amount of time the object is allowed to exist before it disappears is vanishingly small for large objects. Even if something like birds did appear out of nowhere, they would be gone again in much less than the blink of an eye. So everything in the universe is a particle and a wave at the same time. The universe existed in 10 to the power of 500 different potential states when it first formed, all with different physical constants and laws, for no reason at all. One of these states was our universe. It appeared from nothing. This is allowed in quantum mechanics as long as the whole thing vanishes again very, very quickly. But we're still here. A quantum-sized universe must disappear again very quickly unless something grabs hold of it during its brief virtual existence and inflates it very quickly to larger than quantum size in a hurry. From comparatively the size of a grapefruit to the size of the whole solar system in under a second. This is another reason why there had to be a one-time event called inflation. So everything in the universe is both a wave and a particle at the same time. When it was very small, smaller than an atom, the entire universe behaved like both a wave and a particle too. The universe existed in 10 to the 500 different potential states in its early form, all with different physical constants and laws because of its waviness. One of those states was ours. Something that small can appear from nothing as long as it vanishes again within a very brief time. Something like our universe could last longer, that is, become real instead of virtual, if energy is applied. Inflation. Using the principles of quantum mechanics, the start of the universe does not appear to be a miracle. It began as a quantum-sized fluctuation and virtual reality with a large number of other virtual universes. Our universe did not disappear, though. It was instead seized by inflation and became real and permanent. It was inevitable that at least one universe would do this out of the billions and billions that were there at the start. one with laws and dimensions favorable to supporting life. Now let's compare what science's conclusions are to that of Judaism. Of course, quantum laws exist within our physical universe, but we are now being told to accept that quantum laws exist outside of our universe. That would make them infinite. Why not some other laws? We don't know. But quantum laws had to exist without space and time for the universe itself to appear from nothing. Quantum laws must be infinite. Science says something infinite must have existed for our universe to form, which is precisely what Judaism says. Judaism says there has to be an infinite source, God. And don't forget, science says there had to be inflation. There is no physics yet to really explain that, but it had to happen. It was a one-time event that had to occur, and it was critical. The Torah also specifies there was a one-time event that had to occur for the formation of the universe, and it was critical. As I see it, both science and religion conclude similar things. Both science and Judaism say we do not have to depend on chance. Both say there is an infinite source requirement. Both say there was a one-time event described by science as inflation. The start of the universe, according to both Judaism and science, are in close agreement.